Welcome. This is a video for Math 246. I'm covering applications of differential equations. So the applications we're talking about, another word for them is what people sometimes call word problems. And here's just a very, very high-level brief outline of the kind of problem we're talking about. We're going to be given a situation where we're given a word problem which describes some system, like for example, the first example I'm going to be doing is water pouring into a tank. And it's describing something that's changing. And for example, water going into a tank, the amount of water or the amount of salt in the water in our example. And we're interested in the rate of change of something. And the word rate there is a big tip-off because that involves derivatives. And since it involves derivatives, the equations describing such a system are going to be differential equations. So given this word problem, the first challenge is to convert it into a differential equation. And sort of part of the same thing, but part B is to figure out what the initial values are and then solve the equation. And what's typical here is that solving the equation is, well, we've reduced it to a problem that's already been solved. We've talked about solving equations, and so that's usually not the hard part. The challenge is the first part, just figuring out what the relevant differential equation is. And in a sense, it's converting the words of the word problem to a differential equation. And that's what we're going to be focused. That step is what we're going to be focusing on mostly. Okay, so as I said, the main step in this process is finding the differential equation. And really the first thing you have to do is identify the variables that you're going to be using. It's often overlooked, but that's once you decide what your variables are, that's half the battle. And once you have the variables, then the next thing is to express the relationships between them. Excuse me, how they're changing, and how they're related to each other. And once you've done that, then usually it's possible to write down the differential equation that you're going to need to solve. So here's a simple example. Well, I'll do a few examples. So first of all, let's look at an example of the following type. Let's say that you have a 500-gallon tank. Okay, and it has water in it. It has 200 gallons of water. And in that water is 100 pounds of salt. So there's a certain concentration of salt in the water. Now we're adding water to the tank. We're adding a mixture of salt and water, 1 pound of salt per gallon, and that's flowing into the tank at a rate of 3 gallons per minute. On the other hand, we're taking water out of the tank, and that is to say the thoroughly mixed water is coming out of the tank at 2 gallons per minute. So the total amount of water is going up because more is coming in. And but the question is about the amount of salt that's in the tank. And the problem is stated as the following: write an equation for the derivative, the rate of change of the amount of salt in the tank at any given time. And that is to say the total weight of the salt in the tank. So it's, and okay. So what was that? Sorry, I didn't get the question. Let's go over that again. So let's unpack all this information that we're given. So the main thing is we're talking about an amount of salt in the water. That is to say, a weight of salt. So we're asking about the total weight of salt in the water, and that's varying as a function of time. And so the first thing we should do is decide one of our main variable is going, let's call it S of t. So it's S of t is varying with time. And let's define S of t to be the total number of pounds of salt in the tank at time t. So at time 0 it's 200, and then it's increasing. And we want an equation for ds dt. How is that's what the question is. Please give me a formula for ds dt. Well, what's causing it to change? There's salt going in, and that's making the weight of salt go up. And how's that happening? Well, we're adding. Well, I'll come back to that. There's salt going down because a certain amount of salt is being taken out of the tank, and so it's a combination of those two factors that we have to figure out how that affects S of t. So let's do the increasing part first. How fast is salt being added to the tank? Well, let's see. The water's 1 pound of salt per gallon of water, and 1 pound of salt per gallon, and it's 3 gallons per minute. So that says, in terms of the salt, it's 3 times 1, which is to say you're adding 3 pounds of salt per minute. So that's pretty straightforward. That's a constant rate, 3 pounds per minute. Okay. Now, what about the amount of salt going down? Well, there's 2 gallons per minute going out, but how much salt is there in 2 gallons? Well, that depends on the concentration. That depends on S of t. So this is a little bit trickier. So let's see. We have 2 gallons per minute going out. How much salt is there in 2 gallons? And that's what we need to know. Well, let's see. The concentration of salt is the amount is pounds per gallon. It's how many pounds of salt there are in a gallon of water, and that's S of t, which is the pounds of salt, divided by the volume of the water at the given time. I'll call that G of t for gallons of water. And both of those things are varying, but whatever. That's the concentration at a given time. And S of t, well, that's what we're trying to solve for. So we don't try and put in a formula for that or anything. That's just going to be part of the equation. So you just leave that as it is. But G of t, we'd like to know. And G of t is elementary. What is G of t? G of t is the number of gallons of water at time t. Well, let's see. You're adding 3 gallons per minute, and you're taking out 2 gallons per minute. So ignoring the salt, you're starting at 200 gallons, and you're adding a gallon per minute. That's just the water, ignoring the salt, because 1 is equal to 3 minus 2. So G of t is 200 plus t. Okay, so now we're getting close to having a differential equation. This concentration is, well, S of t is what it is, and G of t is 200 plus t. And that's a concentration, and so the amount of salt going out is that times 2. And it's very helpful to put the units in here. So this is pounds per gallon. So S of t over 200 plus t pounds per gallon. And the rate that it's going out is 2 gallons per second. Excuse me, per minute. And the units cancel, and you get 2 times S of t over 200 plus t pounds per minute. And this illustrates one of my favorite techniques in these problems, which is getting the units right. A rate is supposed to be pounds per minute. And if you, this is a very helpful way to check that you're doing the right thing and to guide you towards what the right formula should be. I highly recommend keeping track of your units and making sure they work out correctly. So in any event, that's how fast the salt is exiting the tank. Okay, so what does that mean? So let's see. What's the rate of change of the amount of salt? Well, there's a plus term, which is this 3 pounds per minute that's being added, and there's a minus term, which is this minus 2s of t over 200 plus t. And there you go. That's the differential equation for ds dt. So let's, we've got our answer. ds dt is 3 minus 2s over 200 plus t. So the question was to write down this differential equation. So we're done. That's the answer. It's quite possible that the problem would have gone on to ask some other things. So, for example, to solve it. So let's just do that as a little exercise. How would you solve this? Is this, oh gosh, this looks terrible. It's not separable or anything, is it? Let's see. So I'm just writing down. You weren't asked to solve it, but if you were, let's see. Is this solvable? Is this linear? Let's see. Maybe it's linear. How do you tell if something's linear? Well, there's the SDT term, and there's an S, which is okay for a linear equation. And let's see, you're allowed to have a function times S. Well, that's what we have here. We have 2 over 200 plus t is multiplied times S. And that's a perfectly good function of t times S. And so you can rearrange this equation in the following form: plus 2 sorry, there's a sign error there. That should be plus. ds dt plus 2 over 200 plus ts is equal to 3. And that is a linear equation and pretty easy to solve. I'm not going to take the time to do that, but that's a linear non-homogeneous equation. Okay, let's go on to look at another type of example. This is a common one in differential equations, that is to say population dynamics. So this is the situation where you have a population of something, people or bacteria or fruit flies, and the population is a function of t, so you write it as p of t, And the standard thing is that the population is changing, and the rate of change of the population depends on the population. And the most common thing is that it's proportional to it. Sort of basic population model is that the rate of change, the rate of growth of the population is proportional to the population. The bigger the population, the faster the growth. And how the constant of proportionality, R, is something that you might need to figure out. And there are variants of this. Maybe it's not just a constant times p, but it's some function of p. Or maybe there's also a homogeneous term, g of t, and other similar related things. So let's look at the basic example of this. You should really think of the general case as some sort of perturbation of this. dp dt is equal to r times p. The basic population model, the rate of growth of population is proportional to the population, and there's some proportionality constant. So this is a very easy equation to solve. It's one of the very first ones we did. We'll just run through that very quickly. It's separable, so you write it as dp over p is equal to r dt, and you integrate both sides, and you conclude that log of p is equal to rt plus c. And then you exponentiate and rename the constant, and you get the solution that p is equal to c e to the r times t. So this is exponential growth. The population increases like an exponential, and how fast it is determined by this r. So here's a very basic example of this. Suppose I told you that I had a population of something, and it satisfied this equation. And let's say, which is quite common, you don't know what this constant r is, but I'm going to tell you something, which is that every 10 days the population doubles. So that's a property of exponential growth, which is that the doubling time is constant. You know, if in 10 days it doubles, and then the next 10 days it doubles again. And suppose I tell you that the number 10, you can find r, and you can also find, the second part of the problem is find p of t, assuming that I've told you that the population right now is, say, 1,000. So let's go through how you use this information to solve the problem. So let's see. We know that the solution is c e to the rt, and we don't know c or r, but we do have some information. So the first part of the problem is this doubling time fact. So how do we use that? Well, let's see. The population doubles in 10 days. So what does that mean? Well, let's say this is time 0. At time 0, the population is c e to the 0, which is to say c. And the population in 10 days is c e to the r times 10, which is to say, and it doubles in that time, which is to say it's 2 times the original population, which is 2 times c. So we've learned something. Setting these two things equal to each other, we see that c e to the 10 times r is equal to 2 times c. And one of the really nice things about this is the c cancels. It doesn't matter what your original population is. The r is the same. It only depends on the 10. And e to the 10r is equal to 2. So that tells you that 10r is equal to log of 2. therefore R is equal to 2 over log 10. Excuse me, misspoke there. Log 2 over 10. Okay, so that's half the problem. We figured out R from the doubling time. So that says that P of t is C e to the 1. I'm sorry, I'm totally miswrote that here. 1/10 log 2 times t. And we know that P0 is 1,000. Well, that tells us C. So given that fact, the solution is P of t is equal to 1,000 e to the 1/10 log of 2. And again, I miswrote 1/2 should be 1/10 log of 2 times t. Okay, let's look at another example. This is an example of mosquitoes. And let's say that you have 250,000 mosquitoes. I'm not sure how many mosquitoes that is. It's a lot. And suppose left to their own devices, the population would double. The population would double every 3 weeks. Except they're not left to their own devices. There are some birds, and the birds are eating a certain number of mosquitoes at a certain rate. They're eating 80,000 mosquitoes per week. So the mosquitoes are, the population's going up, except that the birds are eating and going down, and those two factors are sort of fighting each other. What's the population of mosquitoes after 2 weeks? Well, let's see. What's the solution here? Well, the equation is, well, first of all, if there weren't any birds, we'd have the standard equation, P of t, dp dt is equal to R times P. And as before, we know that the solution, well, we're trying to find out what R is, and we can do that from the doubling time, just like before. I'll write it just very slightly differently this time. P of t is C e to the RT. So P of 3 over P of 0 is, what's P of 3? C e to the RT. Well, it's equal to 2. So that says that C e to the R times 3 over C e to the 0 is equal to 2. And that tells you right away that e to the 3r is equal to 2. E to the r times 0 is 1. So that says that e to the, so that 3r is log of 2, and r is 1/3 log of 2. So that's very much like the previous example, which is different with a 1/3 instead of 1/10. Okay. All right, so that's R, and so now, but that would be what would happen if there were no birds. So what happens with the birds? Well, here come the birds. The equation now becomes what? It becomes dp dt is equal to, well, let's see, there's this R times P, except there's this minus term now, which is minus 80,000. Per week. And so so here's the equation. dp dt is equal to 1/3 log of 2 times P minus 80,000. And that's it. That's the differential equation. There's no more undetermined coefficients in it. And let's see, what's the initial condition? The initial condition is that P of 0 is 250,000. So we can now solve this equation. It's going to have one unknown, one variable of integration, and then we will use the initial value to get rid of that. Okay, so let's see how that works. Well, so let's see. Well, this is first order linear. dp dt minus the constant times p is equal to minus 80,000. And this is linear, first order, non-homogeneous. So remember, you solve this by multiplying both sides by an integrating factor. And the integrating factor in this case is very easy. It's you look at this 1/3 log 2, and you take an antiderivative of that, and since that's just the constant, you get e to the well, it's exponential, so e to the minus 1/3 log 2t is the integrating factor. So you multiply both sides of this equation by that, and I'm going to skip a few steps here. And this example is in the notes, so if you want to see the details of this calculation, see the notes. When you multiply by the integrating factor, you conclude and after doing the integral, you conclude that e to the minus 1/3 log 2 of t is equal to this constant times e to the minus 1/3 log 2 of t plus some constant. And let's see, you solve for c by plugging in at time 0, the population is 250,000. And again, I'll skip just one or two steps, so let's go to the answer. What you get at the end is p of t is equal to 80,000 over 1/3 log of 2. Let's see, plus 250,000, that's the c, minus this number here, and that's all multiplied by e to the minus 1. Excuse me, e to the 1/3 log of t. Let's think about that. Let's see. It's maybe helpful. Well, so now we want to know what's the answer at 2. So you plug 2 into this, and you get your computer, or you look at the notes, and it turns out that there's about 193,000 at time 2. And here's the graph of the population. It actually goes down, and after about 5.5 weeks, it goes to 0. Okay, there's one final type of example which you should look at in the notes, and that's force motion equations, Newton's laws. And so please see the notes for that. And that concludes today's video.